All right, hi everyone. Welcome back to section 6.3. And in this video, before we get started on solving differential equations with the singular point centered power series, we wanted to find what exactly regular and irregular singular points are. 'Cause there's two types of singular points, okay? So a singular point is said to be a regular singular point of a differential equation if the function little p of x equals x minus x naught times p of x, and q of x minus x naught times q, capital Q of x, are both analytic at x naught. Analytic, remember, is just a fancy word for being like, nice, no domain issues. Okay, so a singular point is regular if there's no domain issues for these like little p of x and little q of x, all right? Um, And a singular point is not regular, meaning irregular, if it doesn't meet these criteria. Okay, so once again, we're still just an introductory differential equation class, so we're just going to be focusing on singular points, okay, which allows us to use the Frobenius method. We need a regular singular point, but it's good practice to identify regular or irregular singular points. Just in case you have to take this in upper division or in grad school, that you kind of have a little bit of background. Maybe you could look back on these notes to see like what regular and irregular are, okay? But let's go ahead and start classifying with an example, okay? So here we go. We have the following differential equation. Determine if singular points are regular or irregular. Okay, so we have x squared minus 4 y double squared y double prime plus 3 times x minus 2 y prime plus 5y equals 0. And so what we want to do here, we want to get p and we want to get q, right? We want to get into standard form. And that's y double prime plus p of x y prime plus q of x y equals 0. So what do I got to do? I just got to divide both sides by that x squared minus 4 squared. Okay, so here I'll say, you know, get into standard form. All right, so what we would have is y double prime plus 3 times x minus 2 all over x squared minus 4 squared plus 5 over x squared minus 4 squared equals 0. Okay, so let's see. We can actually break this down a little bit more, like y double prime plus 3 times x minus 2. Well, that x squared minus 4, that could be factored into x minus 2 squared times x plus 2 squared. And same thing with 5 over x minus 2 squared times x plus 2 squared. That'll equal 0. And we can cancel out this x minus 2 and then one of the copies of x minus 2. So what we're left with is y double prime plus 3 over x minus 2, x plus 2 squared. All right, and the 5 term is just the same. Sorry, I'm forgetting my y's. Y prime, y, y prime, y, y prime, and y. Oops. Let me write a little more off to the right. Okay, so that's our setup. Um, A couple things we can note about it is that, this is that P of X. This is that Q of X. All right. And in the denominators, we have X minus 2, X plus 2, X minus 2, X plus 2. So we're going to have some domain issues, and those give us our singular points. So what I'll say here, down below is, you know, notes X equals 2 and X equals negative 2 are singular points. Okay. And P of X equals 3 over X minus 2 times X plus 2 squared. And Q of X equals 5 over X minus 2 squared times X plus 2 squared. Okay, so we have P, we have Q, we know our singular points. Now we want to see if these X equals 2, X equals negative 2 are regular or irregular singular points. Okay, and the way to do that is to see if little p of x and little q of x are both analytic at those singular points. Okay, meaning there's like no domain issues whatsoever. So let's go ahead and try that out. So we now will come over here. I'll say we now test p of x and q of x at each singular point to determine if x equals 2, oops, if x equals 2 and x equals negative 2 are regular or irregular singular points. So let's try it out. Let's try out x equals 2 first. All right. So for x equals 2, okay. So here's the idea, right? For x equals 2 to be a regular singular point, x minus 2, meaning like x minus x naught, can appear at most to the first power in the denominator of p of x and at most to the second power in the denominator of q of x. Okay, so where am I getting these first power, second power? Well, the definition is like, here we have x, think about it like x minus 2 times p of x, x minus 2 squared times q of x. I'm gonna need some things to cancel out so that I won't have any domain issues at x equals 2. So for little p of x, I would need x minus 2 to the first power, so that would cancel out. I would need x minus 2 at most to the second power in little q of x, so that would cancel out. Okay, so that's sort of the criteria. All right, but let's see live to see what exactly we mean. Okay, so what I like to do is call this a check. All right, so little p of x, what is it? It's x minus 2 times capital P of x. So this would be x minus 2 times P of x is 3 over x minus 2 times x plus 2 squared. Okay, and that works out well because the x minus 2's cancel out. And what I'm just left with is 3 over x plus 2 squared. Okay, so there's no domain issues at x equals 2, right? So P of x is analytic, meaning no domain issues at x equals 2. Okay, what does that mean? No domain issues at x equals 2, right? Because it's just x plus 2 there. No issues. All right, so same idea with little q of x now. All right, so it'd be x minus 2 times capital Q of x. So that's x minus 2 squared, right? I'm getting it from up here. X minus 2 squared times Q of x, which is 5 over x plus 2 squared. Well, that works out well too. The x, so excuse me, I'm forgetting x minus 2 squared. All right, so yeah, that works out well. The x minus 2 squareds cancel out. And so what I'm left with is just 5 over x plus 2 squared. So what does that mean? That means q of x is analytic at x equals 2, meaning no domain issues at x equals 2. All right, so both p of x, q of x are analytic at x equals 2. So what does that mean? Therefore, x equals 2 is a regular singular point. Okay, great. So x equals 2 is a regular singular point. Okay, so we got one. We got to check out another. We got to check out x equals negative 2. All right, we still have to see if that's regular, irregular. Let's try it out. So for x equals negative 2, okay, what I can see already for q of x and for p of x and q of x is that x equals negative 2 provides a expression x plus 2. Well, that appears to the second power in p of x and appears to the second power in q of x. All right, so it's going to cause some domain issues for p of x. All right, let's see exactly what that means and let's write down that language a bit. So for x equals negative 2, since x minus negative 2, which is the same thing as x plus 2, appears to the second power in the denominator of p of x. And what's p of x again? It's 3 over x minus 2 times x plus 2 squared, right? It's appearing in the second power. Then I guess I can leave that circled. Then x equals negative 2 is an irregular singular point. Okay, so that's us identifying it, but let's go ahead and check it out. Like, what exactly does that mean? So let's check it. So little p of x equals x plus 2 times capital P of x. So that'll be x plus 2 times 3 over x minus 2, x plus 2 squared. Okay, sure, the x plus 2 and a copy of the x plus 2 cancel out, but I'm still left with x minus 2 and x plus 2. All right, I'm focusing on x equals negative 2. So this x plus 2 in the bottom gives me some domain issues at x equals negative 2, right? If x equals negative 2, this denominator goes to 0. So since I have some domain issues there, therefore, we are not analytic at x equals negative 2. So therefore, x equals negative 2 is an irregular singular point. Okay, so we have some domain issues at x equals negative 2, so it's an irregular singular point. Okay, so we could do the check. You could also just notice right away like p of x has x plus 2 to a higher power than just 1, right? And that's one of the criterias from the definition. Okay, so that's how we check for regular and irregular singular points. But like I said, we're just going to be focusing on regular singular points, okay? Most specifically centered about 0, which is nice. But just want to give us some background about this just in case you have to see this later on in your math career. Okay, but thank you for watching, and then I'll see you in the next video where we'll be trying out some power series solutions. Okay, take care.